Maybe we should do it in high school since he is a teacher, so we should have.
So you guys already figured out
So the number of tables.
Or 18.
Give me like a number sentence. So how we doing?
So what do you guys think?
Oh, I see one over here.
Let's test it.
So where do those go? Yeah, that's these two and
I'll be back tomorrow.
Bye, Luciano.
so these probably need to go. Number of tables.
What would happen if we wanted to add two more?
This one, yeah.
I still don't know how.
Oh, you mean to the side, not when you said inside, I was thinking.
Oh, no.
So that's gonna move to the side of the. Okay.
So it has the area.
So should I put a one?
Okay.
I would say yes.
So I mean, I think where you were headed with it was, makes sense to me that each, so there's
Just
a
this
number
here
of
all.
tables,
Well, this is our verbal description. Well, that's okay. Yeah, that's okay.
you know, for each table,
So the functions.
for each table you guys inside, that you have to do all of that. And then every time, then the long side, that's just two.
Bring more boxes.
Each table basically has two sitting across from each other. Then that's this part. And then this
Because this one represents our seats. So 4 chairs times the number of
describing
tables.
that was where you're going, or is that?
Got about 3 minutes.
Yeah.
Yeah, sitting across from each other.
Two more seats.
You want us to go beyond this sentence, so.
So instead, we have the two, because that stays fine. My two is fine.
You all need to space for it anymore?
Space for us.
Is this a good description of it, or do you want to say the number of tables multiplied by 3?
Okay, once you finish your chart, everybody on their phones, y'all need to put them on the wall and we're going to discuss them. I mean, unfortunately good. One more thing. got about 30 seconds and we're going to discuss. All right, so when the students discuss their work, this is called a public display of work. And it's important that they have a public display of work because it holds them accountable. It gets them up, I'm gonna make you go up to your chart, you're gonna have to explain to me what you did and why, and you're going, well, not just to me, but to the class. And everybody in the group has to talk, all right? So choose whichever part you wanna talk about. And then you can ask the group questions about your particular chart. Okay, so it makes the kids accountable for understanding. It also lets you know who really doesn't understand. For instance, if Faith sat there and let Mark and Ross do all the work, I will know because she won't be able to tell me anything about the chart. Okay? And we do it in a way that doesn't embarrass them. And you have to be careful. It's a fine line here. So you have to be careful when they do things up on the wall, just as Denise was talking about with the big circle, little circle. So then as a teacher, you have to know what questions to ask to help that one child who is a little confused answer some questions, all right, so that they walk away thinking they know something. So we're going to start, I think, with where are the squares? Okay, we're going to start with the squares. So all three of y'all up there. Yay, squares. Okay. Go ahead and tell us what y'all discovered.
Okay, well, what started with, when you put one square for the table, then we had 4 people that were able to sit around it, and then as we added 2 tables, we still had the 4 people, but then we added 2 additional people. When we had 3, then we had 2, 2, 2, and then still the 2 people on the ends.
Okay.
4 tables, we had the 2, 2, 2, and 2, and then the 2 people on the ends, and then 5 tables, we just added that again, the 2 across from each other, 2, 2, 2, 2, and then 2 at the very ends.
Okay, so can you tell me about your table?
Yes, ma'am. So in our table, we list the first in our T chart, the number of tables we have, and then how many people can sit at each table.
Okay, and those were your ordered pairs?
Yes, ma'am.
1 table, 4 can sit,
Yes, ma'am.
2 tables, 6 can sit, and that matches your picture.
Yes, ma'am.
Okay. And so the graph, sir?
So we graphed it, the horizontal axis was the number of tables and the vertical axis was the number of people, and it just shows the ordered pairs from the T chart in the graph.
And y'all remembered how to graph, because we did that last week. Graph, yes. Say
Yes.
Just an aside, how many of you are not a math major?
Sorry.
How many of you are not a science major?
right now.
Okay, do we still lead teachers that are math majors and science majors? We just have to remember that we can ask questions too.
Yes, yes. Teachers would love to answer your questions. Okay, so I see your graph, which is nicely done. Tell me your rule.
Our rule is 2n plus 2.
2n plus 2. Tell me your verbal description. The verbal
Okay.
description.
So we kind of followed, so for every table, you had 2 people that were sitting across, and then in addition, you had the 2 people that were on the long ends. So that was the 1 table. For the 2 tables, we went to 2 people across from this table, 2 people across from this table, and then the long ends. And so that's how we wrote our verbal, as for each table, there's 2 people sitting across from each other. In addition, there are 2 people seated on the long ends of the combined table.
Okay, so the number of people would be equal to what?
So
Your rule doesn't have an equal there. So we need an equal there. So the n represents what?
Number of tables.
The number of tables, okay. So the number of tables times 2, where that 2 represents which people?
So you're
You
sitting
see
across
what
from
she's
each
doing,
other.
she's doing a very good explanation.
Yeah.
The ones from across, like the children would sit, there were 7 in my family, 5 kids and 7, so I know exactly what you're talking about. All right, and so the 2 represents the number of people sitting on the sides of the tables, And what does that other two represent?
The ones on the end.
One's on the end.
One's on the mom and dad?
Mhm.
Okay, all right. Later, once everybody talks, we'll talk about your graph a bit more, okay? All right, thank you. So let's do the triangle next. And don't worry, it's not long. Picture? Sure.
Okay, so we started with 1 with 3 available sides, and every time we added a table, it added on the available sides that weren't pushed up against another table, so there was 2 added on to the 3, so we had, I'm sorry, but it added 1. After that, it adds on 1 more because of the available
Okay,
side.
let's back up. You said it added 1. I don't know
The
what
total
it
number
is.
of people, the total number of people,
When we added a table,
Okay.
it added 1 person to the table every time we added a table.
Every time you added a table, it added 1 more person.
2 people. It added 2 people.
Okay, you sure? I'm not saying you're wrong. I just want to make sure that you're sure.
We are sure.
All 3 of you are sure.
it added 1
Okay,
to
don't
the
use-
number of
don't
people
use-
before that.
Don't use it.
The total number equals 1 more from the previous.
So every time you add a table, 1 person is added.
Yes.
One.
From the number of yes, but I'm saying from the number of people. So we have 3 people here, and then when we pushed up a table, it added 1 more person
To the total.
to the total.
The total of what?
Number of people.
Number of people. So every time you add a table, it added how many people?
1.
1. Okay. Okay, so that's the picture. You know what, it's very hard to say without using it and that, and just, people are supposed to know what you're thinking. And that never happens, because you don't know what I'm thinking right now.
Mm-hmm.
Because I'm actually thinking about the storm that's in Houston, and I'm wondering if I'm gonna get home safely, okay? So, don't use pronouns, use nouns, and be very explicit. That's that sloppy language we've been talking about. And every teacher does it, but they have to be trained to think about what they're saying. It's not just in math, it's math, science, everywhere.
Right.
I was in a science, I supervised the THECB people, which I don't know what that means, the paraprofessionals who are allowed to do their student teaching in the summer because they're working during the year. So I supervised those in the summer. So I was in a classroom on Monday, and I was listening to the cooperating teacher explain genetics with Punnett squares. And I know Punnett squares, I do. Can't pronounce them, but I know them. And she never used a noun in the whole 20 minutes she was talking. And the kids who had already failed their ELC biology test were totally lost. And of course, she was the cooperating teacher, so I couldn't say anything to her. That's not my job. But then when the student got up there, I was correcting her constantly about using pronouns, because I'm telling you, those kids didn't have a clue what she was talking. Most of them were ESL. Most of them were bored to tears. They didn't want to be there. They didn't care that they failed. So it was a rough group. So anyway, so back to you. Say it one more time for me.
You just Okay, so in our picture, in our sequencing, every time we added a table,
Yes.
the total number of people that could sit at the tables increased by 1.
Nicely said. So where do you see that in the table? It doesn't have to be the same person talking all the time.
I'm tapped out, you.
So it's in our ordered pairs right here. You see it as a pattern. Well, you see on the T chart, sorry, number of tables. We listed the number of tables and then the number of people on this side.
Okay, teacher. So as you go down the number of people, what's happening to that?
It's increasing by 1.
By 1,
But
which
we also-
matches what she said.
Yes, but we also noticed in the T chart that the number of people is number of people is 2 more than the number of tables
The number of people is always 2 more than the number of tables?
in our set of
Yes.
5. Yes,
In your set of 5? Okay. So then what is your rule?
Her rule is T plus 2 equals P, which is the number of tables plus 2 equals P, the total number of people.
Number of people. Thank you for not saying just P. All right, so looking at your graph, it looks like it's done correctly. Okay, all right, nice job. So now we'll go to the, what do we have left? Hexagons and trapezoids? And triangles, parallelograms. Let's go to parallelograms next. Go on. Ruby's up.
So, Luciano made this wonderful presentation of our trapezoids representing tables. Parallelograms, I'm sorry.
She's science, y'all.
How did you know? And then we have these small representations of people. So this is our drawing. Do I need to continue explaining more of this?
I understand the drawing.
Okay, perfect.
Okay, so go to the table.
Here is our T table. What we have here over to the left-hand side represents our number of tables. So we have 1 through 5. And on the right-hand side, we have number of people. So that could sit comfortably. So we have the maximum, Lori actually pointed that out because we could have one table with 3 people. But for our representation, it's the maximum number of people.
Okay.
So we have, at one table, we have 4 people that can sit at maximum at that table. What we noticed when we had 2 is if we continue.
To what?
If we added another table,
Thank you.
we would lose 2 people. And that's because when you put them together, you lose that area in between the 2 tables.
So that should be 2 then. If you have 2 tables, it should be 2 people, because you lost 2.
We lost 2.
So, but you have 6 up there.
We do have 6 because you still have the sides where 2 people could sit on those 2 areas. So you lose the inner portion, but you don't lose the outer portion, so you can still see 2 people.
So you're doing like this. So I hear
Yes.
you're talking about mom and dad. Right? The ones on the ends?
The ones on the ends, mom and dad.
Okay.
And so that led us to the discovery of the 2n plus 2 equals t function.
Rule. You're in
Rule.
4th grade. Yeah, function's not a word.
Rule. So where n would represent the number of tables, so 2n, and then t would be the number of people, and that's what Lori said. So I had to check for myself. So I said, all right, so she put 2n, so 2 times 2, so if we use 2, would be 4, plus 2 would be 6. So 2 tables, 6 people. So Lori was correct in what she said.
Thank you, Lori.
So we noticed for every 1 table, we can sit 4 people at maximum.
Okay. So your table looks like their table.
Our table does look like their table.
How
And
can
what
that
table-
be? They're different shapes.
And what table is that over there?
No sidebars. This is a square.
The square table, because I think that we have 4 sides, or they have 4 sides, and we also have 4 sides.
So because the shapes are both quadrilaterals,
Yes, ma'am.
you're going to get the same number of people for
Yes.
this specific number of tables. Okay. Do y'all agree with that? Faith, do you agree with that?
I think the data on both those charts prove that it's true.
Well, it proves it for the square and for the parallelogram.
Correct.
But there are other other quadrilaterals, right?
Yes.
Such as what's
The
another
trapezoid.
The trapezoid. So we'll have to see if that's true for every quadrilateral. It better not be an adult knowledge thing. Yes, ma'am.
Well, since I'm in 4th grade and I started with 1 table meeting 4 people, if I added another table, you would think there would be 8 people.
You would.
You really would.
Why is there not?
Because when you put the tables together, that's where we lost 2 places to sit.
So that's what Ruby was talking about with the losing.
Right,
Ah.
right. And as we kept going, we kept noticing that we're still losing the same number of places. So I'm wondering if the restaurant couldn't have done something different.
Such as?
Placed maybe at the points.
You know, that's an interesting topic.
And
We
then
can
not
investigate that tomorrow.
Nice.
You know, we only have like 45 minutes, or I don't know how long you have. So that would really be something that would be really nice to investigate, but not today. Thank you, Laurie. Great point. Laurie's really good at thinking of fourth grade. No, I didn't mean that to be ugly.
How big is your circle now, Lori?
No, that's pretty big.
I have a pretty big.
That was actually a compliment.
It was.
Yeah, because she's really good at it. It's hard to think like a child. It really is hard. Okay.
They taught me.
Yeah. Okay, so I made her a juvenile. All right. So going on, your graph looks kind of different from theirs, even though your table is the same. So we will come back to that in a minute. Okay? All right. So what's next? What do we have? Trapezoids? All right. So Ross? And kind of quickly, because I'm kind of dragging this out. Okay, Ross, you're the lead.
I messed up the picture, so.
So he should have to explain the picture.
Explain the picture, Martin.
So I didn't draw the people and I clumped them all together, right?
Yeah.
But essentially, when you have one table, 5 people can sit there, 2 at the bottom, 2 at the ends, and 1 at the top.
Okay, all right.
That is represented in our T-chart, in that the number of tables, we had 1 and 5, but when we grew to 2 tables, the number went to 8.
Okay.
3 tables, it went to 11, 4 went to 14, and 5 tables, 17.
Okay.
And then our rule is the number of tables times 3 plus 2 equals the number of people. And that works the same on our T-chart.
On your T-chart, so you checked it. So the number of tables times 3 plus 2 is equal to the number of people. So let's look at this one. That had multiplication and addition. Did y'all's have multiplication and addition in your rule? Good. Did this one have multiplication and addition? No, just addition. And theirs says multiplication and addition. Okay. Now, y'all are teachers for a moment. I went over there and I talked to that group because they were thinking
We are
about the
special.
rule. The trapezoid is really interesting. And lost my train of thought. Where was I going with this? Y'all should know.
You're the teacher and you
Uh,
walk
well, we must
around.
have to- I had to make them show me in the model that they still had built where that 3 was. They said the number of tables times 3. I had to have them show me where that 3 was because they were kind of not thinking correctly, right? Not that you weren't thinking correctly, but they were kind of wondering about things. So they figured out where that 3 was and where that 2 was, much like y'all did. So in your linear, your children now again, in your linear thing, your linear picture of that thing is horrible. Where would those 2 be?
That'd be mom and dad on the end.
That'd be mom and dad on the end. Y'all noticing a pattern about these things? Mom and dad are always at the end. Thank y'all. Nice job. So who's left?
We are.
Hexagon.
You got it.
So in our graphic representation, each hexagon could, or for the first table, it could seat 6. As we went on, we noticed that you could add 4. I'm saying this wrong now because I'm nervous because I don't like math. I'm sorry.
You love math.
Want me to say?
Yes.
Repeat after me. You love math.
I love math. It just makes me anxious.
So the first one had 6, but as you added a table, just like the other ones, we're losing the 2 people in the middle. And then we have the mom and dad on the edge again. So when we did 2, we had 10 people total. 3 gave us 14. 4 gave us 18, and 5 gave us 22. And we noticed that there started being a pattern that if we looked at just the hexagon, we always had 4 people sitting at the table each time we added the hexagon, and then we just had mom and dad always on the end. Thanks.
Yeah.
That was a great job.
So what was your rule?
So our rule was for 4 people, or it would be 4 times the table plus 2.
Okay, 4 times the number of tables plus
Plus 2
2
gave
gives
us
you
Number of people.
the number of people. Make that a complete sentence. Okay, nicely done. So, thank you, ladies. Y'all are all so good. Thank you. We're not quite through though. Thank you for bringing back what Miss Laurie was asking about with the losing the 2 in between. That was a nice connection that y'all made. Did everybody lose 2 in between?
No, they just lost 1.
You just lost 1. So the shape makes a difference?
They lost 2.
Well, when they first added the table, when they went to 2 tables, they only lost 1.
I guess if you,
No, we just lost.
or if you assume that
Every other
everybody
one.
had 3 at each
Table.
side.
If you hold it apart.
So it would be losing 2.
Losing 2? The one at this table and one at this table? Yes. Okay, so everybody lost 2? Wonder why? I'll let y'all think about that. And we've already decided the 2 on the end were the constants. Ross even used that word when I was over there. The 2 on the end are the constants. And what changes is that number in front of the n, because it depends on the shape of the figure. Okay? All right, so I want to look at the graphs. Most of y'all, and this is not 4th grade, okay? You're in middle school now. Most of y'all did not connect your dots in your graph. This group did, okay? So when should you connect the dots and when should you not? You're in middle school now. You're a little bit more knowledge. All right, you're in 9th grade now. I don't remember what it's called. Yes, ma'am?
You connect the dots when it's continuous and you don't connect the dots when it's discrete.
What's
You said when
continuous?
it is continuous. What is continuous? What's the
When
it?
the function is continuous, you will connect the dots because you can look at the parts in between the points that you have. And it's discrete if in between the points doesn't make any sense. And if you look at the linear pair in between.
Okay, so what I hear you saying is they did not connect theirs, so their data is discrete. That's what we call data that you don't connect, discrete. So it's either continuous or it's discrete. And why is this discrete? Well, what is down here on the horizontal axis? What is that representing? The number of tables. Am I going to allow you to cut a table in half? Or a person in half? No. So we would never have a point right there that fits our particular situation, right? Some situations it does, but not for tables and people. So this is discrete data. So should the dots be connected or not? No, they should not be connected.
And of course,
We have that handout? Okay, but in a minute.
But my line's
Because-
really straight.
That's okay. I told you were 4th graders. 4th graders would not know that. You are a 4th grader, that's fine. But when I bumped you up to 9th grade, 8th grade, you know, that's when they're gonna get into that. Now, Miss Ruby, do you want to explain your graph?
Oh, our dilemma?
Yes.
So,
This is very interesting, a great conversation with this.
so Lori, she's a smart one in our group.
Now,
the rebel.
I agree with that.
She does a lot of questioning. She said, what do you think of 3 people sitting at what table would they sit at? Because I suggested no people could sit at no tables.
Okay.
And she said, well then how, if we had 3 people, where would they sit? I said, well, they would have a table too. So we said, where on the graph would we put that? So we went up to number 3 people. We said they would have a table. And then what about 2 people? So then we put a point there. And then we said 1 person would need a table as well. So then we noticed we had points in between instead of that trend or pattern that I noticed.
So you're telling me at one table, you could have 1 person, or
Yes.
2 people, or
Or
3
3.
people, or 4 people, which is why when you presented your graph, you said we talked about the maximum number of people,
Yes.
right? And we all just assumed it was the maximum, okay? All right, so, go ahead.
Same thing with the 5 people being at 2 tables.
Okay.
And so we started noticing points running up, running vertically, at every, I guess, maximum number of tables.
Mm-hmm.
And then we noticed it again with the second table. And so we noticed these points started running vertically, then shifting over.
Okay. So you have 4 dots on one,
Yes.
then you have 4 dots on,
On the next had we,
I don't know how many dots you have, but several dots on the 2,
yes.
and then on the 3.
Yes.
So that is not a linear graph at all, is it? Not linear. Lori, what is it called?
Me?
You're the nice one.
Piecewise.
Piecewise. So that right graph comes in pieces. So when is that taught?
Probably pre-calc.
Probably pre-calc. So y'all
Although
are
I
very
did
advanced for
algebra
4th grade.
But we didn't find a function.
Well, is it a function?
No,
It's not a function. Why is it not a function?
because of the vertical line
It's
test.
a vertical line test. All right, I just want to clarify, that is not a function. It's a rule, but not a function.
It's a relation.
It's a relation. Okay, so y'all did so good. So now your principals again.
But your 4th graders may question that.
They will.
They might. What happens
GT
if there's only one person? Do they go to the table? So that's why we brought it up.
But can't one person sit at a group of 5 tables?
Nice. Can it?
Like, it's like-
Can one person sit at a group of 5 tables?
But they won't be seated there.
You got PHP on Sunday and there's lots of tables and you just sit down.
So but we'll have to make the stipulation that the restaurant would not allow that. Right. So if you're actually gonna do this with your teachers, make those stipulations, okay? So, we've already talked about that. So, thinking of this as the classroom, if an outsider had walked into this classroom, what would they see or hear? Hang on. I forgot my own rule. Annalise.
The person that would observe us, I think would see, they would observe that we were up and having conversations. They heard noise. They didn't see us in rows, sitting and getting,
Okay, so what was the teacher doing?
walking around,
Walking around, was I just walking around with my head in class?
asking questions.
Asking questions, so, and now I can look like I'm just walking around with my head in the class. I really can, my pre-service teachers haven't figured that out yet, that when I'm walking around, I'm really listening, because sometimes they're still talking about their date last night. But I am really listening. So, so the teacher walking around listening, asking questions when appropriate. Okay? I even complimented some groups when appropriate, okay? What were the students doing? All the work. They were doing all the thinking and all the work. So that's what's important in the math and science classroom. We can't have them in rows, and we can't have them, just sitting and getting, as she said. So, how did this fit in? Did I prepare you adequately on the before? Hopefully I did. I'm not perfect. I'm not saying I did. So, did we have a rich conversation during the lesson? I had several. I had some with this group, I had some with that group, and I had some as a whole group. Okay? And this can be either a 10-minute lesson, it can take the whole class period, depending on how far you want to go with it. Alright? So this was just a model of a lesson. Now, I'm going to switch gears and talk about patterns. Denise and Sandra have both already talked about patterns. Patterns are extremely important to notice because algebraic thinking is generalizing patterns. That's really all it is, generalizing patterns. That's the goal of algebraic thinking, and you all know that algebra is the gatekeeper. A student that fails Algebra 1 is much more likely not to graduate. So Algebra 1 is the gatekeeper. I don't know why, because it's a lovely course, I love it to death, but anyway. So the importance of data tables, from kindergarten up, students should be using data tables. In K1, the teacher would do it, they're all over the carpet, The teacher draws the T-table, she pulls the answers from the students and fills in the table. In grades 2 to 3, the students can begin to record their own T-tables, simple T-tables. And from 4th grade up, the students can actually draw the T, label it themselves, and make their tables, right? So this is an example of a table. This is the number of dogs versus the number of eyes for normal dogs, okay? Lori is sitting there, so I had to add the word normal. She is out of the box thingy, okay? So here is the table. Most people notice, most students and teachers, notice the table going, the pattern going down. That's called a recursive pattern. That's an important pattern for them to notice. They do need to begin noticing the pattern going down. But we don't want them to stop there. They have to notice the pattern going across. I think it was this group that I came to and I said, what did you do to the 1 to get the 5? Well, we could have added 4. Well, that didn't work for the 2 tables. Well, we could have multiplied by 5. Well, that didn't work for the 2 tables either. So it had to be a combination of operations. Okay? So finding the rule going across, that's called the explicit rule. And they've got to get to this stage by Algebra 1, and really now by 8th grade. They've got to be able to get to the explicit rule. First thing they'll notice is the recursive pattern. And for those of you that were here last summer, you remember that as being the finite differences. But they've got to get to the explicit rule. Now they can use the finite differences to get to the explicit rule. What's the recursive difference here? What's going on? You're adding 2. Do you think that has a relationship to this 2? Say yes.
Yes.
Absolutely, it does. And of course, this is very simple because the finite differences here are all 1. If those are not all 1, then this is a little different. Okay, but you don't need to know that right now. Okay, so this is important and it begins early on. You remember in elementary school when you do skip counting? Suppose you had a calculator. I'm not going to make you do this, but you could do this on your phone. And I want you to make 50 and start with 2. Make 50 and start with 2. So the kids are adding 2 every time and they're continuing to press. This is one time when the calculator is good for problem solving. So it should be in the students' hands. We're not just trying to find rote answers with the calculator. We're solving a problem, okay? So they continue pressing, and it's similar to skip counting. There are the T's for skip counting in Kinder 1, 2, and 3, okay? Many times they do it on a hundreds board. Now suppose the kid starts with 3, or you tell the kids to start with 3, and continue pressing. They're still skip counting, right? Can they get to 50 if they start at 3? Why not?
Because 3 is an odd number and 50 is an even number. So every time you add, that's not gonna work. Three is, I'm not gonna keep going.
Okay.
You can't multiply 3 to come up to equal to 50.
So there's nothing you can multiply 3 by to get 50?
Yes, there is, probably, but there's not a whole number that you can multiply by 3 to equal 50.
So 3 is not a factor of 50?
Correct. So
It has nothing to do with even and odd, because 5 is a factor of 50 and can be, even though it's odd? Okay, very nicely said. So these are some of the questions you would ask, you know, for these types of problems. It's a problem-solving situation. Yes, they have a calculator, but they're not using the calculator just to find an answer. They are thinking. Right.
I was just gonna say, I can get to 50.
From starting with 3.
Sure, I just go beyond 50, but I certainly can't get to it.
Okay, there's that problem again over there. 1 can sit there, 2 can sit there.
But I'm
3 can
thinking
sit
like a kid.
Yeah, you are.
A kid is not going to differentiate that I need to get exactly to 50
Well,
without going
Some
beyond.
kids.
Some
aren't.
kids.
Some kids are. You're right, Lawrence. Okay, so let me show you why this is important. If they're skip counting by 2, here's the input-output table that they could be making after they do their hundreds chart, and there's the graph. So what teaks are these? K through 8, 1C. Grade 6, grade 7, grade 8, Algebra 1. So So even beginning in kindergarten, remember I told you the kindergarten teacher could be making that table and they just fill it in? So if the kindergarten teachers start doing these kinds of things, maybe not the graph, but start doing these tables and not horizontally, vertically, then that's planting those little algebraic seeds in their heads. And then when they get to algebra, they're not gonna go, oh, well, I don't like that stuff, I don't understand it. I guarantee you, if you had a teacher that had been doing this from kindergarten up, you would love math as much as I do. Yes.
I was also looking at, even specifically for this skill, looking at social studies data and how our kids, when they get to tables and charts, even in social studies, they don't, it confuses them.
Yes.
You know, and this is a, skill that we can develop in all content areas to get kids to really try to tackle.
Both math and social studies teachers talking to each other about it.
Yeah, what is this data
Thank you,
trying
Mark.
to tell me?
Yeah, it does. It confuses people. They're not used, well, they can analyze it in a math class. They go to the social studies class and they don't think they can analyze it, but they can. So this was the, starting with 2. So if you started with 7, is 7 a factor of 50, Faith?
No.
No. So you're not gonna get exactly to 50, right? So this would be the table and it does not start at 0, it starts at 7. So that leads to the algebraic idea of the y-intercept not being 0, not being the origin. See how easy it is? Kindergarten. Okay. Algebra is kindergarten stuff. So the difference in procedural knowledge and conceptual knowledge, I'm gonna kind of hurry because I think we're kind of running late. Procedural knowledge is, yes, I can find slope because my teacher told me how to do it. Conceptual knowledge is I understand what slope is and I understand the importance of it. Okay? Conceptual and procedural. This is a procedural knowledge. You have an idea here, you have an idea here. They're not connected. You don't see any connections. You might have a new idea here which might connect to that one, like maybe addition and subtraction, but it doesn't connect to any of the other things in your little head, in your schema. This is conceptual knowledge. All those connections. Now still some things may not be connected quite yet, but they're gonna get connected eventually. Okay? So, I'm gonna go ahead because I get kind of preachy with these things and y'all can read this when they give you the PowerPoint. You notice the PowerPoint is not in there. I don't give them to Sandra until the end of the day because I don't want you to have to answer ahead of time. So that's that. So, see, I get kind of preachy. So when you're doing math and science, you should always begin with the concrete first, the manipulatives. When you introduce a concept, it's got to be started with concrete. After a while, students may not need the concrete anymore, and they're ready to go to pictorial. Drawings, charts, graphs, pictures, diagrams, tables. Okay, the pictorial. And then eventually they get to the abstract, which is a number sentence. Numbers and words are abstract. Numbers and words are abstract. Yes,
Sandy, we have our chart.
oh yeah, the charts right over there.
And we're gonna come back to that, but
Can you speak to, I've heard you guys say numerous times, the difference between this process and teaching concepts and skills?
That's a science thing.
well, kind of. We have actually a chart that we're gonna go through with this. It's gonna give some more explicit instruction, but the idea is that you have to start with the concrete experience with kids. So obviously math manipulatives are concrete. In science, most of the lab materials that you're gonna use are gonna be concrete. So someone has to start with a concrete experience, but it could also be kinesthetic. For example, they could be modeling molecular motion, the difference between a solid, a liquid, and a gas. And so kinesthetically, so it could be a concrete experience. And that would be before they would use any technology, before they would look at somebody else's pictures. The pictures that they draw themselves would be concrete. So they could diagram, or they could draw a picture that illustrated, I'll go back to the molecular motion of molecules, what it looks like between a solid, a liquid, and a gas, but they're drawing it, whereas if they're looking at it in a textbook, it becomes pictorial, it's more abstract, it's less concrete with them.
And see, in math, we do not call pictures if they draw themselves out concrete. Those are still pictorial. They just draw themselves. But more conceptual than a picture in a book, because they're doing it themselves. So there's some differences. I think he was asking about your example about teaching them how to use a microscope.
Oh, okay, that kind of fits in with something we're gonna talk about later with direct construction versus inquiry.
That's what I was getting.
Yes,
So that's later, okay.
coming,
So
a coming attraction.
this was an inquiry lesson, an activity.
And how do you know it's inquiry? It's a very easy answer or question. Did you know the answer before you started? Then it's inquiry.
Okay, so that sequence may take several days. Y'all went from the concrete to the pictorial to the abstract quickly, because y'all really could not forget your adult knowledge, even though I told you to try, right? But this lesson with students, depending on the grade level, could take several days. Could take several days. It may not, but could. Now, here's the important part about the student display. Public records of students is very important for them to explain, even if they don't want to, like Ms. Laurie. You know, they have to get up and explain what they're thinking, and it helps them implant it into their head even more deeply. Okay, it helps them conceptualize it even more deeply, because we don't want them to be like these examples. Frank and Levi decided in 2003 that there are 3 levels of justification. The first justification is appealing to an authority figure. My teacher said so. So tell me, how do you divide fractions? Hang on. Faith, I'm sorry, it really is you. How do you divide fractions?
What time are we supposed to do? How do I define? Divide fractions. Oh, and it's fractions, really?
We have 1/2 divided by 2/3. How were you taught to divide that?
Oh, to do the little, I don't know, there's some trick that you can do there.
There it is. There it is. And let me phone a friend for you.
Thank you.